Hi, I'm Jonathan Aldrich. Let's talk about unions. A union is a data type that can hold one of several different representations, which we call variants, at runtime. Every instance of the union is exactly one of the variants, and so it's kind of an OR relationship. Unions are used for two main purposes today. In systems code, unions allow the same bytes to be interpreted in two different ways, or perhaps more different ways. Unions also represent alternative variants of a data structure, allowing us different options of representation. There are two main forms of unions. In the tagged form, the runtime uses a tag to keep track of which variant you have and allows you to test the tag. In most cases, the language will enforce consistency so that you can only read the data in the format that the tag specifies. The other alternative is untagged unions. In this case, you have to know which variant of the union is being used. You can do that by rolling your own tag, basically adding another construct to a surrounding struct or a Boolean or something, so you know at all times what the variant is going to be. But this can be unsafe, because if you read one variant and you wrote data in another variant, then that data may not be meaningful when reinterpreted the other way. Let's look at unions in C and OCaml to illustrate these differences. C has untagged unions. So here we have a struct address, and we'll have a Boolean that tells us whether it's a street address or a PO box. Then we have a union that says, okay, in one case it's a PO box and we'll keep track of an integer there. In the other case, it's a street address and we'll keep track of a care pointer. The union is named address details so we can access it. In OCaml, the language will track the tag for us. So here we declare a type of address, and we've got two different cases, PO box, which holds an int, and street address, which holds a string. Internally, there will be a flag that tells us which one of these is being used in every case. Let's see how tag unions can be tested with pattern matching. In OCaml, we have our type address, as I showed you before, and then we can create an address by using the PO box constructor with the integer that goes into the data. So that fourth line is assigning into adder an address that happens to be a PO box. And so the runtime will keep track of a tag saying, hey, it's the PO box and not the street address. Later on, we can get the text from this address, and we can do a matching. Let's say we've forgotten that this was a PO box. Well, at runtime, we can do the match, and this match will test at runtime what is the flag. Is it the PO box flag or the street address flag? And we give two cases. So if it's a PO box, then the number inside it will be bound to the variable num. And in this case, we can produce a string, which is PO box, and then turn the number into a string. In the other case, we have a street address, and the street address is already a string, and so we'll just return that. I'm not showing an example of accessing tag unions in C, but basically you can access them just like fields. So if we have an address, we could say adder.addressdetails.PO box, and then we get the PO box. Hopefully we know that it is the PO box. If we want to know for sure, then we can just test the isStreet flag. Let's talk about union layout. Part of the point of unions is that they allow two variants to share the same memory. So imagine that we have an element structure that's been extended with a union at the end where the variants are controlled by the metallic tag. So we have our information about an element with the name and atomic number and so on, and then if the metallic tag is true, we have the source and prevalence of this element, and if it's false, we have the lifetime of the element. We can extend our grammars for types, values, and expressions to support unions. Here we have a union construct that has a set of constructors, so these are the names of the different variants of the union, and each constructor has a type, which is the type of data that is held when the union is that variant. The values are simply constructors with the value for the type that goes with that constructor. And then for expressions, we can create a union by naming a particular constructor and passing in an expression as the value for that instructor. And then we can have a match statement. We're going to use tagged unions in this case. So we'll have a match statement where we match an expression E, and then we have a bunch of branches for different constructors that bind the data to some variable X and then express some expression E that can use the data from the constructor because X will be bound in E. We can also extend our big step operational semantics. So creating a data type or a union just involves evaluating the expression that's inside the constructor, and then we get a value, which is the constructor with the value for its data inside. And when we do match, then we're going to evaluate the E, which is called the scrutiny, and we'll turn it into a, it'll evaluate to some constructor, which has a value inside of it. And then we'll choose the particular constructor, so this will be the ith constructor, so we'll choose the ith expression and the ith variable x, and we'll extend the variable environment with a mapping from xi to the value that was inside that constructor, and then evaluate the corresponding expression in the right branch of the match statement. This will produce a value v prime, which is the value that results from the entire match. Here, match is an expression, which is common in functional languages that have tagged unions. They tend to be expression-oriented rather than statement-oriented. How do we type unions? Well, here are typing rules for creating a variant from a union and matching over a union value. When we create a variant from a union, we type check the side that's the expression that's inside, and we find out that it has some type tau, and then we create a union that is just for that constructor C and the type tau. You may ask, well, aren't unions normally a union of multiple different constructors and types? That's true, but in fact subtyping will allow us to make this a part of a larger union in our theory, and we'll see the subtyping rules on the next slide. We type check the match expression by first identifying what is the union type of the scrutiny expression. So our first premise checks the scrutiny, E, and finds out that it is a union type of a number of different constructors. Again, we use the overline notation for multiple constructors. And then for each of those constructors, we assume that X has type tau, add that to the environment gamma, and we check that the corresponding expression E prime has some type tau prime. Now notice that all of the X's and taus and E primes can be different, right? For every branch of the match statement, we might have a different type for the constructor, so X has a different type. The names of X can be different. X is just a stand-in for whatever the programmer wrote. And of course, the expressions can be different. But they all have to return the same type tau prime, because no matter which branch is taken, we want to be able to predict what the result is and have that be consistent. Just like records, unions also have width and depth subtyping rules. So the depth rule is similar to the one for records. If tau is a subtype of tau prime, then a union of tau and other taus like it will be a union of the constructors with type tau prime. We also have a width rule, but it's actually the opposite of the one for records. Basically, the width rule says that if we have one union as a subtype of another, then that union is a subtype of the second union with more cases added. Why is this? Well, a subtype must have fewer variants than its supertype, because if we're going to treat it like the supertype, then we might case analyze it, and we want to make sure that all the cases are covered. Well, if we're case analyzing the supertype, all we know is the supertype's cases, and so the subtype has to have fewer cases than the supertype. Let's check our understanding.